2022 question number 3. This is the cubane question, which you may have come across before. This is a really great question. It's really challenging, but really interesting, and I think the challenge is pitched just right. You know, it's difficult, but attainable if you really think about it. In the actual test itself, it might be a bit of a struggle, but I think we can work through it all pretty cleanly now. So, state the molecular formula of cubane. Here it is here. That should be pretty straightforward. It's just a cube, so there are 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8. So I know there are going to be 8 carbons. So normal skeletal rules apply. And then you can see that each of these carbons is identical, and each of them is bonded to 3 other carbons. 1, 2, 3. So they're all going to have 1 hydrogen sticking out. So at each of these corners, there's going to be a hydrogen sticking out. Oops. So C8, H8. Then, my favourite part of the question, you're given these different cubane-based molecules, and then you're asked to identify the number of peaks in the carbon-13 NMR. So essentially how many unique carbons there are in each of these. So we can start with this one here, that's 1. So there's no other carbons like that one. Then number 2, the one that's bonded to the acid. And then this is now bonded to 3 that are all the same. Okay, and you know, you want to come up with your own method. This is the way that I like to do it, by just numbering them, and that allows me to see how many I've got and which ones are the same. So if I go along from 3, I'm going to get number 4. So number 3 comes to number 4, number 3 comes to number 4, number 3 comes to number 4, number 3 comes to number 4 at the front there, and then that leaves me with 1 right on the opposite side, which is 5. Oh, sorry, I was supposed to do cubane. I mentioned earlier that cubane was 1. Let's just keep a track of these. So cubane is 1. Cubane carboxylic acid, I've now established, is 5. Then I've got these 3 different dicarboxylic acids. So 1 and 1, those are both the same, and both of these carbons that are bonded to those are both the same. And then from 2, I can go either way, and it's going to be the same top or bottom. All right, so I'm going to have 3 there, 3 there, 3 there, 3 there. So all of those 3s are the same. And then I'm left with these 4s over at the other side. Okay, so that gives me 4. Now this is, you know, you need to be able to picture this cube in your head. Maybe if this gets a little bit difficult, maybe, I don't know, if you've got like a Rubik's Cube or something else that's cube shaped, you can sort of hold it in your hand and try and see what's going on. But you should be able to see that this 4 here, you know, it's the one that's opposite the carboxylic acid corner, and down here opposite the carboxylic acid corner, and these are both the same. All right, same logic here. The carboxylic acids are the same, then they're bonded into the cube the same, 2, but now they're both on top, right? So it's easy to think that this might be the same as this one, but here the carboxylic acids are along the same edge, whereas now they're on opposite corners. Okay, so that's going to be a 3, that's going to be a 3, and then the 2 is going to go down to a 4, the 2 is going to go down to a 4, and then 4 goes across to 5, and 4 goes across to 5. So that one is also 5. And then the last one, this one looks pretty symmetrical, probably won't be as many carbons here. 1 and 1, 2 and 2, and then I go up from 2, 3, across from 2, the same, across from 2, the same, and here it's all symmetrical. So if I go across from 2, I'm doing the same thing, because that's the same, that's the same, that's the same. Okay, now that's the way that I would do it. Hopefully you can see that. I think if you're struggling to see these, you know, try and draw them out yourselves and number them yourselves. But if it's still really an issue for you, this probably isn't the best place to start. You probably want to go back and just practice with simpler molecules, identifying unique carbon atoms. You know, maybe something like if you just have a square and this is, you know, can you identify how many unique carbon atoms there are in that molecule? Can you identify how many unique carbon atoms there are in that molecule? I think if you're struggling, trying to do it on this is going to be a bit of a challenge. Okay, so that's that first page done. Then we get into the synthesis. So the start of the cubane synthesis is shown below, and we're given molecular formula, excellent, molecular formula, excellent, molecular formula, excellent. That is going to be very, very useful for us. Now, we want to find A and B. So A is here, and it says A was treated with 3 equivalents of Br2 to form B. And in B, which has the molecular formula of that, each of the 3 bromine atoms are exactly 3 bonds away. Okay, so fine. We can come to B later. Let's just look at A first. So it's probably worth writing out the molecular formula of this, which is going to be C5, and there's 2, 4, 6, 8, H8O. So you can see that I'm adding 2 carbons. And the 2 carbons I'm adding are going to be these 2 carbons here. So I need to get these 2 carbons into this molecule, and there are going to be 2 oxygens, and then I'm going to have 12 hydrogens. Well, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So essentially this molecule incorporated into this molecule, preserving the single bond with both of the hydrogens on, and having 2 oxygens. Now at this point, you know, if you know what's going to happen, right, it's going to be, you know, it's going to be nucleophilic attack from this oxygen to the carbonyl carbon, and then it's going to repeat. But if you look, it's always worth just having a glance down later on in the synthesis. What else can I see? And you can see in D, I've got this thing here, all right, which I do not have here. So would this be able to give us a clue as to what's going to happen over here? And the answer is, of course, yes. So if I now keep my 5-membered ring, which I've already said I'm going to need, but then if I add this thing to it, which seems like a reasonable thing to do, will that give me the correct molecular formula? 1, 2, 3, 4, 5, 6, 7 carbons, 2, 4, 6, 8, 10, 12 hydrogens, and my 2 oxygens. All right, so that is the molecule that I'm looking for. Then it says A is treated with 3 equivalents of bromine to form B, and in B, which has got this molecular formula, so what's happened, you can see 7 carbons, 2 oxygens, 2 oxygens, 12 hydrogens becomes 9 hydrogens and 3 bromines. So all I'm doing is replacing 3 of the hydrogens with 3 bromines. And it says each of the 3 bromine atoms are exactly 3 bonds away from the 2 oxygen atoms. Okay, so how can I get exactly 3 bonds away? So if I put the bromines up here, maybe I should draw out a rough version that I can show this on. If I put the bromine, one of the bromines up here, well, that's not going to work for me, because yes, it's 1, 2, 3 bromine, 3 bonds away from this oxygen, but it's only 2 away from this one, so it can't go there. So then we go the other way. 1, 2, 3. I put the Br there. Now, I'm 1, 2, 3 away from this oxygen, and I'm 1, 2, 3 away from this oxygen. So that works for me. And they're all the same. They're all like that. So the other one goes there, and the other one has to go there. I mean, it doesn't matter. It's symmetrical. It can go either side. All right. So Br, and then B was then reacted with XX sodium hydroxide. This reaction is proposed to proceed via intermediate C, which then reacts with another molecule of itself to form compound D. It's all really important information. I always say this in these videos, that you should, whenever I don't read the information, that doesn't mean you don't read the information. You should always read everything, because there's going to be key bits. Just like up here, exactly 3 bonds away, and they've bolded that, but it's from both of the oxygen atoms. if you don't read that extra bit, you're not going to get the right answer. So the reaction from intermediate C to D is known as a Diels-Alder cycloaddition. Fantastic reaction. Okay, one of the all-time most interesting reactions you can get. So we have now we go into the sort of the training phase of the question, where they're gonna show you the general one. They're gonna give you examples to do to make sure you know how to do it, and then you're gonna have to apply it. Okay, classic Olympiad structure. So look very carefully at what's going on here. So the double bond here, the electrons go over here and form a new bond there, but the bond here is gone from a double to a single. Same here. I've got a double bond here and I've got no bond here. And now I've got a single bond, single bond. Double bond here, no bond here. Now I've got a single bond, single bond. All right? So then you're asked to do the practice. So W and X. Okay, well, I can see that this molecule with the two double bonds is like this molecule, and this molecule with the one double bond is like this molecule. But what they've done is they've twisted them round. So it's now, if you were at this position now, it's going to be really difficult, especially if this is the first time you've seen this reaction, to see how this applies to this. So the most sensible thing to do is just to redraw these to look like that. So that is that, and then I'm going to draw this one like that. Okay, and then I would go ahead and do the arrows like they've got. So that one's going to go there. So that double is going to become a single, and I'm going to get a bond here. This double is going to become a single, and I'm going to get a bond there. And then this double is going to become a single, and then this is going to become a double. So you can see, and I might as well just put it into the answer here, that this single bond is now a double bond. This double is now a single. There's now a bond between these two carbon atoms. This has become a single. There's a bond now between these two carbon atoms, and this double has become a single. And then I can add on that, and that. Okay? Fairly straightforward. Then, same again, all right? But they've increased, so again, now they've sort of flipped it round. They've put the diene, the one with the two double bonds over here, and the one with the single double bond over here. Fine, okay, you can't trick me. But they've made this into a ring. Don't panic though, it's exactly the same. So I'm going to draw it out the way that I like it, with my two double bonds here, and then I can just draw in the rest of the molecule. Let's not panic. I know it's easy at this point to think, what on earth is going to happen here, but let's not worry about it. Let's just draw everything out. Okay, and then do the same again. That's going to go there. That's going to go there. That's going to go there. And at this point, hopefully it should now become clear that it's a ring forming reaction. So I'm going to make a ring, but I've already got a ring. So I'm going to have this fused ring situation. So let's not worry about this carbon atom for now. Let's not worry about this one. Okay, let's just pretend it's not there. All right. And in fact, if you wanted to, you could sort of just think to yourself, well, what if I was to do this? Okay, what would that give me? Well, I go there, I go there, I go there. What am I going to get? I'm going to get... That's easy enough, right? Fine. Okay, I can do that easy. But then, I've got this situation. Okay, so where does this carbon go on this structure? Well, I would probably label up my carbons here. Okay, so this is carbon number 1, that's carbon number 1. That's carbon number 2, that's carbon number 2. That's carbon number 3, that's carbon number 3. So you see the new bond has formed between 2 and 3. Then this is 4, this is 4, this is 5. I've got my new bond between 4 and 5. And then this is 6, this is 6. So where is this carbon? Well, this carbon is bonded to carbon atoms 2 and carbon atoms 5. So this carbon we're going to draw like that. Okay, and then you try and see it. you know, you've got this one ring and then you've got another ring coming out of it as well. There will be some fused ring examples later on in the question for you to sort of see an example of. But yeah, this can be quite tricky if it's the first time you've seen it. So let's just draw it in. Fine. And then Y dimerizes via a Diels-Alder reaction to produce the product shown. So here you have this, now you can see, look, so this is a fused ring situation, right? So I've got this ring, this 1, 2, 3, 4, 5, 6 membered ring here, and then I've got 1, 2, 3, 4, 5, another 6 membered ring sort of fused onto it. That's the kind of thing that's going on over here, okay? And in fact, actually in the mark scheme, I think they've got it in a different, yeah, I'll show you it here. So you can see they've got it drawn the way that I got it drawn, but this is sort of, maybe that's easier for you to see how this carbon sort of sticks out. So this carbon here is this carbon here. Okay, right. So why dimerize to form this? Trying to untangle this is going to be an absolute nightmare. All right. And I remember when I first saw this question, I spent a little bit of time thinking, geez, how can I disentangle this to get back to here? And then I realized you don't need to. Okay, it's Y and Y, it dimerizes. So I just count the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've got 12 carbons, which means that Y has got 6 carbons. Okay, and I can see that there is a 6-membered ring. Okay, so, and final piece of information is I know that in order to do a Diels-Alder reaction, I must have 2 conjugated double bonds. So Y is just going to be that. And it has to be. You know, there's no other option really. And if you want, you can sort of, you know, try and convince yourself by doing the Diels-Alder reaction. It's going to be a little bit messy. So if you do it like that, okay, I'll use a different colour here. So, ooh, is this going to work? That's going to go there. That's going to go there. That's going to go there. Okay. And then I can sort of see, I'm going to fuse the 2 rings together. Now, importantly, let's say this is A, and this is A, this is A, this is A. That's now going to bond to B. To B. Okay, so I'm going to come, the new bond is forming between A and B. Okay, so these are both of my B's. And then that's where the new ring starts. This double bond hasn't changed, so that's that one. And then I've now got this carbon and this carbon, which is going to come up, across, and down. Now, does that look like this? Well, you can see this double bond here is like this double bond, then I've got this bit over the top, that's this bit over the top, and then I've got the double bond to one side. Okay, and that's why it's to one side, is because this has to line up with only one of the double bonds. All right. So, as far as you know, training sections go, I think that's pretty tricky. But hopefully you can see how this reaction is working. And then, once all that is done, it then says, based on this knowledge of the Diels-Alder reaction, draw the structure of intermediate C. Okay, so let's go back to intermediate C. Okay. And it says here, so here's C, and it's going to make D. So we've got to work. We know that B looks like this. Fine. We know that D is this mess here. All right. But there's another piece of information here. This reaction is proposed to proceed via intermediate C, which then reacts with another molecule of itself. So it is a dimerization again, just like the last one that we did down here. Okay. So. What I can do is I can just quickly count up the carbons in D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I've got 14 carbons, which is great because over here I've got 1, 2, 3, 4, 5, 6, 7 carbons. So nothing fancy is going to happen, okay? So what do I need to do to this in order for it to be able to do a Diels-Alder reaction? And that is, I'm going to need some double bonds, okay? Now, it should be clear that I can't put my double bonds in this ring, because then the double bond will be to the oxygen. So my double bonds need to go in this ring. It should also be clear that my double bond can't be up here, because this carbon has already got 4 groups attached to it. Okay, so what I'm going to have to do is I'm going to have to put a double bond here and a double bond here. And in order to do that, I'm going to have to get rid of a bromine and get rid of a bromine, which is fine because I go from 3 bromines down to 1 bromine. All right, so that gives me that. And I can just double check the molecular formula. So 1, 2, 3, 4, 5, 6, 7 carbons, 1, 2, 3, 4, 5, 6, 7 hydrogens, 2 oxygens and 1 bromine. So the important, and then if you want, you can sort of look and think, well, is this going to make this? And yes, it is going to make that because the Diels-Alder reaction is going to happen down here, preserving this ring in both molecules. So nothing happens to this, nothing happens to this, and I get the mess of rings down here. The important point is that it is always important to look further ahead in the synthesis and see if you can work backwards or find some clues to where the chemistry is happening. But when you get this, just how down here trying to untangle this was a really difficult task, but I could use other tactics, right? Same way up here. Trying to untangle this backwards, you could reverse the Diels-Alder reaction, but it's going to be pretty difficult to do that. Just in case that is useful for you, just when I say you can reverse the Diels-Alder reaction, let me just take the first product, W. You can, in theory, work backwards just by reversing all of the arrows. And that will give you your 2 products, your 2 reactants. I don't think there wasn't anything down there. So that'll give you your 2 reactants. So in theory, you could work back from here. But, you know, trying to do this, let me just sort of like, oh yeah, I'm going to go backwards there, backwards there, backwards there. It's, you know, I'm going to get myself in all sorts of trouble. So I would prefer not to do that. All right. So pretty good so far. Let's carry on. Compound D reacts with aqueous acid to form compound E, which on exposure to UV light reacts intramolecularly. Thank you for bolding that for me. To form compound F. Right. So, on the structure in the answer booklet, circle the electrophilic carbon atoms in here. So, electrophilic carbons are going to be anything that's a slight delta positive. So oxygen is more electronegative than carbon, so that's going to be electrophilic. And bromine is more electronegative, so those are both going to be electrophilic carbons. The key here being to see that it does suggest, and it's one of those awful ones where it's like, maybe it's 1, maybe it's 2, I'm not going to tell you, you've got to decide. But both of those are going to be potential sites for nucleophile attack. Then, using the frameworks provided in the answer booklet, draw the structures of E and F. Okay, very helpfully they've drawn it for us. And then we want to know E. Okay, so let's have a look. I've got 10 carbons. Here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oof, did I count that right? Let's do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so I'm losing 4 carbons. I've got 2 oxygens, so I've got 4 oxygens here, and I've only got 2 here. I'm also losing 2 oxygens. And I'm given this lovely carbonyl band here. So it should be fairly clear that, you know, why bother doing all this fancy deals out of business if you're going to mess with this part, right? So what we're doing now is we're getting rid of this bit up here. So the 4 carbons I'm going to lose are 1, 2, 3, 4, and those 4 oxygens are going to go down to 2 oxygens, and I've got carbonyls. So the only thing it can really be is a carbonyl there and a carbonyl there in place of my 2 oxygens here. Nothing else is going to happen to it, so my bromines are still there. Bromine is there, and this bromine is down here, and my double bonds, no reason for those to go, so I'm going to put those in as well. And then you will want to just double check the molecular formula is going to work for you. So I already checked my carbons, I already checked my oxygens and my bromines. So hydrogens, are there 6 hydrogens? There's 1 there, 2, 3, 4, 5, 6. Yeah, fine. Okay. Then, now this I think is the most difficult question. It's sort of, if you've got a gut instinct for it, you can just go ahead. But I think this is really tricky. So, compound E reacts intramolecularly to form compound F. And compound F contains 2 4-membered rings. Now they give you this general scheme for the Favorsky rearrangement. Now the Favorsky rearrangement is from F to the cubane structure. So this is the F rearrangement. So the temptation now is to try and work backwards using this reaction mechanism, but that's going to give me a headache trying to do that. So let's go and see if we can figure out a different way. So I know that the molecular formula of this compound F is C10H6O2Br2, right? And the molecular formula of this is also C10H6O2Br2. Now, there's no change in the molecular formula, but I do now have 2 4-membered rings. So the bromines are not going to change. The oxygens are also not going to change. Now, double bonds and rings are equivalent in terms of double bond equivalence. So what that means is, for example, if I had, just over here, if I have 1, 2, 3, 4, 5, 6, 5 hexane, and I want to turn it into hexane, I have to add 1 equivalent of H2. Okay, but likewise, if I've got cyclohexane, and I want to turn cyclohexane into the straight chain hexane, I also have to add 1 H2. So a ring and a double bond are interconvertible in terms of the number of hydrogens. So what that means is, if there's no change in the number of atoms, no change in the number of hydrogens, what I'm doing is I'm exchanging my 2 double bonds for 2 new 4-membered rings. Because if you look in here, there's no 4-membered ring. I've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There's no 4-membered ring, and it tells me that I've got 2 4-membered rings. So I need to now put in 2 4-membered rings. And this is the bit when I did it that I just spent, you know, a really long time trying to sort of work it out to see if I could. This one could, because you're going to start to look like a cube. All right. This one at the back I thought was fairly obvious. So this one here, like that. Okay. So the 4-membered ring that I formed is 1, 2, 3, 4. Okay. And the other one Now this is the one that really threw me, because for a long time while I was looking at this, it seemed like this is the one that should be happening, right? Because the double bond is here, the double bond is here. If I get rid of both of them, then I have to bond those together. But the problem I had was this makes a 5-membered ring. 1, 2, 3, 4, 5. But you can see that in addition to my original 4-membered ring, 1, 2, 3, 4, I've now got another 4-membered ring, 1, 2, 3, 4. And you can see that that's going to be one side of the cube, and that's going to be another side of the cube. Okay. Now, what's really interesting is you can, if you want, you can sort of see how this Favorsky rearrangement is going to work. So that is the answer. All right. Now I'm going to start drawing on my answer. What I want to see is, how do I go from here to here using this reaction scheme here? All right. Now, I've got my bromine, and I've got the carbon that's bonded to is that carbon, and I've got the carbonyl carbon is that carbon, and then what's going to happen is this bond here is going to be replaced with the OH. So this bond is going to break, and then that's going to become my OH group of the acid. And then, and this is the bit where you've got to be really careful, this carbon here is going to take the place of the bromine. So the bromine comes off, and then this carbon then bonds to the carbon that was bonded to the bromine. And I can do the same down here. I've got my bromine, I've got the next carbon, I've got the carbonyl carbon, and then this one breaks. Okay, that one breaks, and then this carbon, the next one along, that then binds to where the bromine was, and the bromine is gone. And you can see, look, what that does is it makes a new four-membered ring. 1, 2, 3, 4. A new one down here. 1, 2, 3, 4. 1, 2, 3, 4. And then my original ones that I already had, which were 1, 2, 3, 4, and 1, 2, 3, 4. So now it's just all 4-membered rings, which is exactly what I need for cubane. Okay, so super tricky to see that, but if you see it, fantastic. Like I said, that one I think is really, it's a nice, you know, I had to sit there and think about it for 4 or 5 minutes before, you know, I could have probably, if I was doing the exam, I'd have just guessed straight away, just like, oh, I think it's going to be that one, it's probably going to be that one. All right, I'm not worried about it too much. But if you sit and you really want to understand it, if you sit for a few minutes, you should be able to get it. So then we do the dicarboxylic acid to the cubane. Fine. Using the frameworks provided in the answer booklet, draw the structures of G and H. SOCl2, by now, this should be fine. All right, that's going to turn this to, it's going to take off the OH, add the chlorine. All right, nothing new there. All right, that's just a standard procedure that you should be aware of. Okay, and then we have this oxygen single bond situation here. So I know that I've got 8 carbons in my cube, 9 and 10. So I've gone from 10 carbons up to 18. And so there are 1, 2, 3, 4. So I'm adding this on, right? But I've now got 6 oxygens. And it should be fairly clear that the only way that can happen is if I get O, 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 like that. Okay, and then the same down here. Now, these steps are significantly easier than the ones we've just looked at. Okay, so that molecular formula matches that molecular formula. Then, just for an extra bit of fun on the end, we have an isomer of cubane, barylene. So this is my barylene molecule here. Can also be constructed using a Diels-Alder reaction. The two sides materials undergo a Diels-Alder reaction to form Q. So Diels-Alder. So let's just do Q first. So again, for this, I would just do it the same way that I've been doing it all along. So that's going to go there, that's going to go there, that's going to go there. So I'm going to ignore this extra bit for now. So I'm going to make my double bond, single bond, single bond. And then this carbon bonds to this carbon. And this carbon bonds to this carbon. But this is a triple bond. So when the triple bond breaks to come down here to form the new bond between here and here, between here and here, that then becomes a double bond. Okay, and then I can put everything else in. O, O-M-E, O, O-M-E, and then I've got my, oh, and this is a little bit, it's going to be a little bit cramped in here. It's going to be like that, that, OH, OH. Not ideal. Now they give me the structure to draw. Okay, fantastic. I was just wondering how I was going to be able to get that down clearly on paper. So now I've just got to map this onto the structure I'm given. So the 6-membered ring at the back, I'm just going to make this one. So I'm going to put a double bond there, a double bond there, O, O-M-E, O, O-M-E, and then this bit coming up at the top is this section coming out, and those have just got alcohol groups on, like that. Okay, so fairly straightforward. Obviously in the mark scheme they've got it drawn like that, doesn't matter. Okay, they're the same. Then an additional ring is formed to give product R. So I go from C12, I'm going to add a carbon, I'm going to take 2 hydrogens, I'm going to add a sulfur, I'm going to form a new ring. So, you know, I mean, if we look at the final product, right, there's nothing's happening down here. The esters are going to get broken in the final step, right? So that's the final step is going to be changing the ester into the carboxylic acids. So now all I need to do basically is just convert this diol situation here into an alkene. All right, so all the chemistry is going to be happening up here. I'm not losing any oxygens, so I maintain both of these oxygens. So my new ring is going to have both of these oxygens in. I'm going to lose these 2 hydrogens. I'm going to add a sulfur. So it shouldn't really be any surprise that. So I'm going to add a carbon and a sulfur. So I'm going to go up like that, and then get my double bond to my sulfur. I know that's a bit of a reach if you don't know the actual reaction that's happening, but it does satisfy all of the pieces of information that we're given. So we've got our extra carbon, we've lost our 2 hydrogens, we've got our sulfur, and we've made a new ring. So I think that's a reasonable situation to work out. You know, there's no other way that you can add those 3 pieces of information together and get a different product. So then we have R, which then reacts to give 3 products, one of which is shown. So this takes away the sulfur. Fine. Compound S is a gas, and compound T, when treated with sodium hydroxide, gives barylene. So like I said, I think this last step here is just going to be the conversion of the esters into the carboxylic acids. And if I work out the molecular formula of this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, C10, 1, 2, 3, 4, 5, 6, 7, 8. Each 8, 0, 4. You can see that I've lost 2 carbons, right? So those 2 carbons are going to be the esters, and I've gone down from 12 hydrogens to 8 hydrogens. So I'm losing, so what I'm doing is I'm going from 3 hydrogens on my methyl to 1 hydrogen on my alcohol. So I'm pretty confident that this is going to be the product I want, but with the ester instead of the carboxylic acid. So then that just leaves us with S, and S is a gas. Now, when I did this, if we think about it, what have I not got rid of? So I've got this, my sulfur. Oh, okay, so my sulfur is gone. So my sulfur is gone. And then carbon and 2 oxygens. So carbon dioxide. I think it's pretty straightforward. All right, so like I said, really fascinating question. I think pitched at a really nice level, really difficult, but if you think about it, it's doable. But also I think, because in terms of preparation for future tests, it's really useful to be able to work through this. Lots of symmetry, lots of different reactions. Really nice. All right, well done.